Và bây giờ chúng ta cùng thử nhé.
The Sano Lab at the Nagoya Institute of Technology have developed a passive walking robot designed to walk using only its own weight, without any motors, sensors, computers or electricity. To begin walking, all this robot requires is a push.
今こちら下り坂の上を歩いているロボットなんですが、動力源はこちらの位置エネルギーだけで歩いているロボットになります。本当にモーターや制御といったものは一切使っていませんので、非常にエコな歩行ロボットというふうに考えています。構成としましては、人のですね、大腿部、下腿部で足首、この大きく3つに分かれています。素材はですね、アルミでできていまして、実際に人のですね、大腿部、下腿部の長さ、またですね、重さっていうのを調整しまして、メカのみで作ってあるロボットになります。
In a walking test last year, this robot walked continuously for 13 hours, taking 100,000 steps and going 15 kilometers. That achievement has been listed in the Guinness Book of Records.
These funny little toys and not so funny mechanical devices that walk on their own are known as passive dynamic walkers. Where's the motor control? Action is always done with purpose in an environment. And the number one feature of our environment is gravity. The point here is that there is an interaction, an unavoidable, ever-present interaction between body and gravity. Perhaps some of motor control is less about control and more about allowing this interactive relationship. As a physical therapist, I was very influenced by these little passive walkers. I used to think of legs as knees, hips, and ankles with muscles. Now I see legs as legs, two struts that hold us up and propel us forward, or backward, or up, or sideways. The knee is just the middle of the leg. It is secondary to leg function, which is driven by the hip and spine, right? Legs swing forward from the hip, and the spine lengthens and rotates to assist. It is not motor control of a knee, but rather it is the leg-trunk world interaction that are the mechanics for control. Maybe there's possibilities here for enhancement techniques in rehabilitation. We can see this leg concept in the next video segment, where roboticists develop a walking robot with leg dynamics as the critical factor for successful control. The determining factor for successful robot locomotion is the angle of the leg to the trunk, or the vertical, and the amplitude of spring forces. Petman is the robot.
So these robots, they're trying to use little tiny motors and do locomotion with the least amount of energy possible. They're looking at energy efficiency. So this robot's at Cornell. It is the most energy efficient robot in the world by far. It can walk 63 kilometers on a pair of D-cell batteries, flashlight batteries, okay? It wasn't using those, but it could. Problem is one gate, one speed, and I could knock it down with this clicker, okay? So it's not agile, but very energy efficient. Here's another group. These are the flat-footed walkers. Asimo's a nice example. Its control method keeps the foot flat on the ground. So they're trying to treat the robot like it's a manipulator. They're doing everything possible to avoid having to treat it as a Segway, something with a rolling contact is what I'm emphasizing there. And you get robotic walking. It's an impressive machine. If it were mine, if it was my work, I'd be waving the flag, there's no doubt. But it doesn't do what we want it to do, which is to really deal with under-actuation, these rolling contacts. Now here's a more serious group of robots, but you'll see why. Almost everybody knows Big Dog, Boston Dynamics. Okay, I'm not going to show you a video of that because we're doing bipeds today. They took parts off of Big Dog and they built they built Petman. Using control principles that Mark Rabert developed at MIT back in the mid-80s, they tried to control the angle of the leg using a very simple representation of the center of gravity, the center of mass of the robot. If you get it just right, you get periodic motion. If you get it too far, it slows down and falls backwards, etc. So they call it foot placement strategy or capture point. Now, if you get it right, you get the best walking I've ever seen in a machine. I mean, by far, this is the best walking. Look at that. I mean, there's a person inside the suit, right? It can't be a machine. That is fantastic walking. Now, here's the next generation of Petman, Atlas. I haven't started the video yet. Training for the recent DARPA robotics trial. So I've started the video. Lights flashing. It has a laser scanner in there, it has cameras, it's calculating the terrain, deciding where to place the foot. So this is how all of the robots moved at the recent trials a year ago. It's calculating. Remember, it's a rescue situation. The house is on fire. The dog's in the back room. Now, once again, if this were my machine, I'd be going, yes, okay? But it's calculating to the millimeter where to place the feet. And that's fundamentally not what you want to do here, okay? So that's the speed that all of them moved at the trials. This robot came in second place. Only a shaft beat it. So here's Mabel, no camera, no sensing of the environment. Our approach is to develop locomotion algorithms that are so insensitive to uncertainty in the ground that it can just plow through rubble. And I consider this superhuman walking. I think a human would do a faceplant here. The robot cannot see the platform. It does not know the platform is there. Look at this. As reflexes built in, my reflex would be to throw out my arms, okay? Because my face is coming next. Now, if we can do that on Marlow, we'll be superstars. We're not there yet. Still pretty far from that. Boston Dynamics is catching up. There's Atlas. So maybe we'll see something really interesting in June at the next DARPA robotics.
No camera, no vision, no program, no knowledge of the environment. Mabel goes forward with reflexes to navigate rugged territory. What is motor control? I have studied and tried to understand forward and inverse models for motor control. I have read into central pattern generators for motor control. There is the one-to-one motor cortex to muscle view of motor control versus the movement for motor control. The hardest for me to grasp has been the equilibrium hypothesis from Anatole Feldman, which right now at this time seems to me to be the most acceptable theory for motor control. The Petman robot's very human-looking locomotion is driven, it appears, by spring force and angle, that is, by an equilibrium point. Mabel navigates rugged territory with reflexes, without vision or motor programs. For me, all of these examples expand my view of motor control and what it is and what it is not. I feel more flexible in my thinking. There are options rather than fixed dogma, which we are all susceptible to. Ultimately, I imagine that an approach to rehabilitation based on these evolving concepts will lead to better treatment outcomes. As science proceeds with explorations and understandings of motor control, there has been a simultaneous development linking action and perception and action and mind. Call it body-mind or embodied mind. We are perhaps a machine with consciousness and learning. Once trained, the machine operates automatically, spontaneously. This includes the good and the not so good motor habits.